Good evening, everyone. Thanks for taking time off of your busy days to join us for this webinar. My name is Henrique Trindade. I'm a teacher at the University of Trás-os-Montes de Douro, UTAD, in Portugal. And I'm delighted to bring you tonight's webinar on importance of water in dairy cows' diets. Our presenter today is Anne Boudon. Tonight, the webinar is being delivered as part of the EuroDairy network. This network includes 14 countries, from Ireland to Poland and Sweden to Italy. It aims to put farmers at the center of practice-based innovation by sharing knowledge and innovations. You can find more about EuroDairy by visiting our webpage, www.eurodairy.eu. Tonight's webinar has proven very popular. We have near 40 registrations from dairy farmers, vets, nutritionists, consultants, and researchers from different countries right across Europe and the world. And we'll run through his presentation, which will take around 30 minutes, and there will be time for comments and questions at the end. You will all stay muted throughout the webinar, but if anyone would like to ask a question, then please type your question into the box on the left-hand side of your screens. I will ask Anne your questions at the end of his presentation, and he will aim to finish up within 1 hour, around 1 hour. I would like to thank our digital manager, Siwan, who is working behind the scenes and will endeavor to keep this webinar running as smooth as possible. But please bear with us if we encounter any technical difficulties. We will try to keep these to a minimum. So without further delay, I'm delighted to introduce Anne Boudon. She's a researcher from the INRA, working in a research unit based in Brittany, in France. She has a background in nutrition of dairy cows with a PhD about ruminal digestion of grazing cows, and is now more specialized in mineral nutrition of cows and sows. Her main areas of interest in dairy cows are the definition of nutritional requirements of minerals, mainly macro elements and water. So please, Anne.
Okay. Thank you very much, Enrique, for the introduction. So first of all, I wish to thank you and Siwan Watson for the organization of this webinar. I also thank all the attendants. It's a first experience for me, but it's also a real pleasure. So my talk will be about the importance of water in dairy cow feedings. It is an area I started working on about 10 years ago. I worked in an INRA research unit located in Brittany, as said Enrique. Brittany is not really known as a region of France with chronic issue of water supply. Actually, our main motivation to work on water supply for cows was mainly that data water footprints for milk started to be released in the press 10 years ago, and we considered that it was useful to update knowledge about drinking water requirements for cows. Today, my talk will be totally focused on animal water requirements. So, the first step of my talk will be to quickly remind you how water is vital and how its content in the organism is regulated. So, on average, the body of a cow contains 70% of water, but the water content is variable during the lifetime, depending mainly on the body fat content. Thus, the body water is lower for a fat dry cow, 55 to 60%, as you can see here, than for a leaner cow in early lactation. The reason of that is that fat tissue contain a very limited amount of water compared to bones or other tissues. Several body pools of water are considered. For a cow, about 70% of water is contained in the intracellular fluid. The extracellular fluid is composed of interstitial fluid, which is lymph, conjunctive tissues. It is also composed of plasma volumes, which represent about 10% of total body water. And it is also composed of transcellular fluid, which mainly consists in water content in digestive tract. As in humans, the proportion of transcellular fluid is very limited, only a few percent. I may use later in this presentation the term of extracellular fluid for both interstitial fluid and plasma volume. An essential function of water in the organism is to ensure the right solubilization and dilution of molecules necessary to their interaction for metabolic reactions and their movement between body pools. It is the solubilization necessity that determines the volume of intra and extracellular fluids. I won't detail all this mechanism. I will just give three main ideas. So the plasma membrane is a delimitation between the extracellular and the intracellular fluid. The plasma membrane is permeable to water, but less permeable to small dissolved molecules. The concentration of non-diffusible molecules on each side of the plasma membrane determine the flow of water. A first driving force of the cell water volume is a high presence of sodium in the extracellular fluid and a high presence of potassium in the intracellular fluid. The presence of NA key ATPase pump allows the maintenance of these gradients. At the scale of the organism, losses of water are necessary for a lot of functions, such as evaporation for thermoregulation, excretion for digestion, or milk secretion for reproduction. It is quite instinctive that all these flows need to be compensated to maintain the body water contents. But how does it work? We saw that the cell can regulate the flow of water across the plasma membrane. However, this capacity of regulation is limited. It is the reason why the extracellular fluid is the major site of regulation of the intracellular fluid. The regulated parameters are more specifically the extracellular fluid osmolarity and volume. These parameters are submitted to perturbations that consist in matter and water flow at the level of the organism, and these flows are regulated with other objectives of homeostasis than the maintenance of extracellular fluid osmolarity and volume. For instance, absorption and ingestion of nutrients are regulated for a large part of them with energy homeostasis, and they increase the amount of solutes arriving in the body, and thus it's a driving force for increasing osmolarity. Another example, evaporation for thermoregulation induce an increase of sweat emission. Sweat is very diluted, and thus it is a loss of water, and it is also a driving force to increase osmolarity at the level of the body. Two major flows allow the regulation of the osmolarity and the volume of the extracellular fluid. They are represented in blue on these slides. They are water intake driven by thirst and water, and water and electrolyte excretion in urine driven by tubular reabsorption. To give a quick view of the regulation loops involved, there are two kinds of regulation nested with each other. The regulation triggered by osmotic signal involves a hormone, the vasopressin, that increases tubular water reabsorption. It also involves the first center of the brain. Osmolarity is very finely regulated by this mechanism. This regulation is more specific to intracellular dehydration caused by loss of water, for instance. The overregulation is triggered by volume signals, and it also involves vasopressin and the brain center of the first. But it also involves the renin-angiotensin-aldosterone system that modulates the renal sodium reabsorption, and the sympathetic nervous system that is responsible of vasoconstriction. This regulation is more specific to extracellular dehydration caused by a concomitant loss of body water and electrolytes. So we can see here that this regulation of body water content is quite complex. A second step of my talk will be to evaluate the water requirements of a cow, or at least the water consumption by cow when water is available at libitum. Many predictive equations of drinking water intake by dairy cow have been published. The list you have here is not totally exhaustive. From this list, we can note that drinking water intake by cow depends on parameters related to animal, to their diets, or to the meteorological conditions. And there is quite a good consistency of the parameters involved between the equation. However, a major issue of predictive equations is the extrapolability of their prediction in various conditions. This depends on the variability of the data used to calibrate the equations, and it also depends on collinearity between predictive variables. To illustrate this point, for instance, dry matter intake and milk production can be very correlated, and the inclusion of both parameters in published multiple regression create a high variability of the parameters associated to these variables between equations. It means that one of these equations can work very well in some conditions, but if you test it in a very different condition, it can work much more or less. After this observation, we realized that we had at the experimental farm of the INRA of Rennes a database of measurement of water balance in cow with a very high variability of diets and production levels. So we imagined that it could constitute a good basis to establish predictive equation of water intake that could be adapted to a large range of feeding conditions with, we expected, a fair enough precision. As you can see on this database, on this slide, these databases involved 342 measurements of water balance in dairy cows during period of 3 to 5 days. And the dry matter intake of cows were comprised between 5 to 27%. For lactating cow, milk production was between 6 and 42 kilos, and about 20% of the data were obtained on dry cows. And when looking at the diet composition, we can see that the dry matter content of a diet goes from 12% to more than 91%. So these conditions were quite huge. Our objective were also to build predictive equation with predictive variables that could be fairly estimated in farms condition. For instance, in the published predictive equation, sodium intake is often used as a predictive variable, but it's quite difficult to estimate it on farms. And we also wanted to build predictive equations with limited collinearity issues, which mean to involve the inclusion, for instance, of milk yield and dry matter intake in the same equation. When we had these databases, First, we established stepwise multiple regressions with the parameters that were less correlated, and we observed, thanks to this, that the dry matter content of the diet, dry matter intake, meal yield, and crude protein content of the diet in forage and concentrate were predictive parameters. However, these parameters were not totally uncorrelated. Thus, we took this equation as a basis to adopt a more mechanistic approach to predict drinking water intake. So the first step, when we look at the set of published equations, it appears that diet dry matter intake is the first determinant of drinking water intake in dairy cows. You can see here experimental results obtained 15 years ago from experiments consisting in feeding dairy cow with partially soaked or dried herbage. As you can see on the figure, when the diet dry matter content increases, the amount of water ingested with the feed decreases. This corresponds to the area between the green and the orange line. At the same time, the amount of drinking water intake increases, which correspond to the area between the blue and the green line. During that time, the total amount of water ingested by the cow, which correspond to the difference between the blue and the yellow line, did not vary. These observations were consistent with the fact that the dry matter content of the diet was not an explicative factor of total water intake in our multiple regression, as you could glimpse on the previous slide, whereas it was a good first predictive parameters of the drinking water intake. From this observation, we retain the following principles in the version of our predictive equations of water published in the INRA Red Book. Drinking water intake was estimated as the difference between total water intake and dry matter and water intake with feed. And drinking water water ingested with feed was estimated as total water intake minus the dry matter content of the diet multiplied by ingestion. When looking at the set of published equations, it also appears that dry matter intake was the first determinant of total water intake in cows and more generally in a lot of farms animals and especially ruminants. This has been well documented. You can see on this slide on goats a very good relationship between total water intake on the y-axis and the digestible energy intake on the x-axis. It is a digestible energy intake, not exactly dry matter intake. It has been suggested that energy intake would be better correlated to total water intake than dry matter intake, but we did not observe this in cows. Moreover, there is no direct stoichiometric justification of that. In cows, as a difference of goat, we also have a high milk production compared to body weight, and it is likely that this significantly contribute to the water balance. But the principle retained is the last version of a predictive equation to avoid collinearity between dry matter intake and milk yield was the following one. We made differences between total water intake and water contained in milk, and we relate these differences to dry matter intake, considering that the amount of water in milk was 88%. When looking at the set of published equations I showed you before, it also appears that the parameters related to the amount of soluble to be excreted in urine were determinant of total water intake. For human, the EFSA defines the renal solute load that depends on sodium, potassium, chloride, phosphorus, and nitrogen food contents. For Derico, this concept is difficult to apply because of the difficulty to accurately estimate sodium intake because of salt blocks. But there is a good correlation between forage potassium and crude protein content, and forage is an important contributor of potassium intake. Thus, we consider that the crude protein content brought by forage in the diet can be a partial indicator of the renal solute loads. So we finally characterize the relationship between the differences between total water intake and water contained in meal, I showed you before, and dry matter intake, and the square of the crude protein of the diet brought by forages. As you can see on the figure here, the relationship between these parameters are quite good. A last problem we have is that we are all aware that water intake also depends on meteorological condition and more specifically on ambient temperature. As you can see on the left side on the slide, as the ambient temperature increase, the amount of heat lost by cutaneous evaporation increase. It means that the cows evaporate more and more water. This is mainly due to the fact that the loss of evaporated water is a way to dissipate body heat when ambient temperature increases above thermoneutrality. It is called the latent heat loss, and 1 liter of evaporated water allows the dissipation of 2,500 kilojoules. We observed from data of water balance measurement in cows that the increase of water evaporation with increasing temperature on the x-axis was totally compensated by an equivalent increase of drinking water intake on the y-axis. This is shown on this slide, and you can see that all the curves of each experiment are parallel to the first bisector. In a lot of published equations, we had some doubt of confusion between ambient temperature and nature of the diet, or and the nature of the diet fed to the cow or dry matter intake. Thus, we wanted to consider both separately in our experiment. For this, we use predictive equation of water evaporation published in the literature, more specifically, equation derived from those of Maya, represented here, to predict the surplus of drinking water for thermoregulation. I propose you not to enter into the detail of the calculations that are briefly given on this slide. I will just show you the range of this surplus. For a cow submitted to a temperature of 27 degrees, an average daily temperature of 27 degrees, we can imagine that the surplus would be on average 20 liters of water per day. This approach is a good approximation of the water requirement when on the cow water requirement with the temperature increasing. It's only an approximation because this surplus of water can also be affected by the level of production of the cows, but we didn't want to complicate more the equation. Just to give you an idea of the validation process of our predictive equation, we build an extra databases from data collected from the literature with about 122 measurements of drinking water intake from specific experiment or water balance studies. We can observe on the left side of the slide that mean prediction error was 29 kilos when the correction from ambient temperature was not considered. When we include the correction about ambient temperature, this mean prediction error decreased to 15 kilos, as you can observe on the right side of the slide. This gives a relative prediction error of about 25%. We also use a database of daily measurement of water intake of a herd of 60 cows in an experimental herd of the northwest of France. We had the surprise to see that our equation under-predicted drinking water intake by about 10 liters per day, which represented about 12% of the observed value on average. We think that the main reason of that is the form of the watering devices. All the data from our databases, and most of those obtained from the literature, were measured with drinking bowls, whereas those from the experimental farm were measured from water troughs. The difference we observed was consistent with direct comparisons of both kinds of devices in the literature. Thus, we made the recommendation that a security margin of at least 15% should be applied to take into account variation of watering condition when applying equations. So the last step of my talk will be to illustrate what happens when water is not available ad libitum. A nice experiment published by Steiger, Burgos et al. In 2001 illustrated that a decrease in milk production is the first response of dairy cow to water restriction. In these experiments, cows had access to 70% or 50% of the drinking water they consumed in ad libitum condition. You can see on the left figure that milk production immediately decreased since the first day of water restriction, and that this decrease was concomitant to a decrease of food intake. After 7 days, the milk decrease was between 1 to 2.5 kilos per day. The fact that both decreases, milk yield and food intake, were concomitant led think that a direct effect of water restriction of milk production is possible. In practical conditions in dairy herds, water restrictions are more likely to be related to restriction to the access of water. A meta-analysis published this year showed reduced milk yield when dairy cows had access to water once or twice daily compared to ad libitum access. The meta-analysis was performed on a database on 16 experiments. On this slide, you can see a reduction of total water intake with limited access to water in most experiments. This led to a median change of drinking water intake of about 13.5%. This had consequences on milk production, which also decreased with limited access in most experiments. However, the median change was quite limited, with only a decrease of 2.6%. However, when looking at the results more deeply, it appears that the change in milk yield of dairy cow with twice daily access to water compared with ad libitum access is influenced by the climate. Actually, the median milk yield decline was only 1.7% in the experiment run in cool climates, whereas it was 15.6% in hot climates. These results are consistent with the idea that a lack of drinking water is very detrimental in hot conditions because it impairs latent heat losses and limits the capacity of adaptation of the cows to heat. Another conclusion of that is that under cool climate, limited access to water can have limited effect on production performance, at least when it is ensured that competition between individuals to watering point is controlled. In conclusion, for the reforms, we can say that ad libitum drinking water supply is necessary to be sure that water is not the limiting factor of milk production. It seems that most of the water necessary for dairy farms is water used to produce the feed, as this can be illustrated from water footprint approach. And a way to save water at the level of an area is first to avoid suboptimal milk producing condition and thus a potential waste of water for overuse such as feed production. To allow ad libitum water access, some ideal rules have been published. We can mention those edited by RSPCA in UK or the Welfare Quality Protocol. So the first rule is that watering conditions should be as close as possible to ad libitum supply, with a water flow of at least 10 liters per minute per cow, a flow that should allow 10% of the herd to drink at any one time. At least, it depends on the recommendation, 4.5 or 6 centimeters of water trough per cow, or a drinking bowl for 10 cows. And each group of cows should have access to drinking water at a minimum 2 separate sites. A second rule is that sufficient water quality should be provided with clean drinking devices and regularly controlled water quality if water supplied is not service water. To finish, I want to illustrate that there is a high variability of watering condition and that progress may be possible. A survey was performed in about 130 farms in France about 10 years ago. This survey consisting in assessing the farms with the welfare quality protocols. You can see at the bottom of the slides what are the criteria of evaluation for this protocol, considering the absence of thirst. So first thing is that the number of functioning drinkers should be sufficient. The drinker must be cleaned, and at least 2 drinkers should be available for an animal. It appears that the criterion of absence of thirst was the most variable among all the criteria of the protocol, with very good but also very bad results. A Dutch survey performed at the University of Wageningen 4 years ago also suggests and confirms a high variability of this criteria in the Netherlands condition. So there may be way to improve the watering system in farms. Thanks for your attention. And